All right. Firstly, I want to thank especially Jayanta for giving me an opportunity to present this work. Coincidentally, I come from Bangalore and I was missing dosas and idlis a lot, so it was a good motivation to come back. I know that this is the Fast Transient Sky meeting, but sadly, I won't be talking about transients. I'll be talking about pulsars. I think you've heard a lot of talks, and my aim through this talk is to convince you that pulsar science still has a lot to offer, and through the results we have found with the MeerKAT radio telescope, hopefully I can convince you that there's a lot to be done in pulsar science. So I think I'll just quickly go through this. I've just probably seen this slide many times. We know pulsars to be highly magnetized, rapidly rotating neutron stars, very compact in size, something like the size of Bangalore, although Bangalore has been expanding a lot. The ICTS is also somewhere way outside actual Bangalore. And we know, if you look at the pulsar catalog, there are 4,300 pulsars, at least. I think there are a little more than that. And so you might ask, what's the point? I mean, there's so many pulsars to work with. Why do you want to still keep searching for more? Well, in reality, because this is a Fast Transient Sky meeting, I thought I'll just quickly say that this is where the pulsars lie. So it's in the transient phase space diagram. So as you can see, quite low energy. So yeah. It's okay, right? Yeah, okay, I was not sure because I couldn't hear myself so well. So okay, thank you. Yeah. So you might think that, okay, why do I need to continue searching? Well, there are actually still a lot of unsolved problems, very interesting problems. Firstly, with the power of pulsars, and specifically what I'm talk about a bit later, which is pulsar timing, you can make precise mass measurements of pulsars. And if you can measure very massive pulsars, that would start putting constraints on the equation of state of neutron stars. That's what is seen here in this diagram. It's mass versus radius, and each curve is a different equation of state. And if you can make a mass measurement, you just put a horizontal line here, and you start ruling out a lot of equations of state. So that is already quite promising. You also want to understand different channels of how pulsars actually evolve. As binaries. Nowadays, we have even found something called eccentric millisecond pulsars, which we don't fully understand. And there are quite a few theories out there, and few of the pulsars are compatible with some of them, and some of them are not. Just like you can, just like the FRB theories, as well as some of the FRBs that we see. It's also a great testbed to do gravity tests. What is plotted here is these measurements from the double pulsar, the only known system where both the pulsars are seen in radio, and both the pulsars of the binary pulsar system is seen in radio. And if you account for the energy loss from gravitational wave damping, you can actually, you get these data points perfectly in line with what is got from GR. So this is again an excellent bed to test gravity and even alternative theories of gravity. And more recently, there has been a lot of noise about possible detection for the gravitational wave background caused by potentially these merging supermassive black holes, which is creating this orchestra of this background. So these are some of the things. Some more things, there's a lot of emission physics we still don't understand. There's a lot of things like intermittency, nulling, so which probably are attributed to these instabilities in the magnetosphere of the pulsar, peripheral evolution. And we have heard some FRB talks here, where, especially from Kenzie's talk just a while back, about observational signatures which show magnetospheric origin. So, yeah, this is a meme which I didn't make, it was from someone else. But the point is, probably there's a link between FRBs and pulsars, and we don't know it. So I'm a believer that FRBs are probably pulsars, but opinion doesn't matter. So that's one aspect. So hopefully I've convinced you that it's important to continue looking for pulsars. So how do we search them? There are few aspects which are common with FRBs. I think you had a workshop, you have gone through a lot of tutorials. There are some standard things that you apply. You start with a filter bank data file. You apply RFI mitigation. You have de-dispersion. And when you have candidates, you apply some kind of machine learning techniques. But the part in between is where it slightly differs for pulsars. You want to be sensitive to binary pulsars. So you want to correct for the binary motion of these pulsars. So you demodulate the orbit before you go into what is known as the Fourier domain, where you take the entire problem into the Fourier, you take a Fourier transform, and anything which is periodic should show up as a bright pulse in the Fourier power. Once you've found some candidate there, you go back to the data and you stack the data modulo this period, which is known as folding. And then you get a bunch of candidates, and then you apply similar things like what you do with FRB searching. That's one approach. You can bypass the whole thing and say, okay, let me just blindly try a bunch of trial periods on the data, and that's what is known as the fast folding algorithm. There are a lot more search algorithms than just this, but this is how typically most people do pulsar searches. I don't have time to get into other aspects of other kinds of pulsar search techniques, but if you want to know more, just have a chat with me later. And after you discover a pulsar, you are going to ask, okay, how do I actually get the science out of it? And this is where the power of pulsar timing comes in. You regularly monitor incoming pulses, and the idea is if you have a precise timing model, if you have accounted for different effects, which is the fact that the Earth is going around the sun, binary motion if it's in a binary, and effects from propagation. If you have a robust timing model, then your observed minus expected of your pulses should look completely flat. You should have something around 0, which is what this timing model shows here. And so the idea is you build a timing model where you're accounting for all these effects. Okay, so with that in mind, I want to introduce MeerKAT. I think probably Kaustubh already introduced MeerKAT to you in the very first day of this week. But just to recap, it's the most sensitive radio telescope in the southern sky, 64 fully steerable dishes, 3 different frequency receivers with a coverage of around 3 gigahertz. You can use the subarray mode where you can use certain fraction of dishes independently of the others. And there's also capability to combine the signals of each of the dishes to form one synthesized beam. So it has the makings of a pulsar search instrument. With that in mind, we proposed this project many years ago, which is the Transients and Pulsars with MeerKAT, where the idea was you target different kinds of sources which can potentially harbor pulsars. And these are the 4 different sources that I'll be talking about here. We are a huge collaboration. As you can see, a lot of institutes, and we are more than 70 plus members. There are 2 PIs, Michael Kramer and Ben Stappers. And there are, for each of the 4 different sources, we have 4 different working groups headed by different people. And there's also a project scientist who takes care of the data management and the processing and things like that. So, okay, I said that we have the makings of a pulsar search instrument, but there are still some more things which are essential, given that MeerKAT is an interferometer. Firstly, you want to be sensitive to pulsars with high DMs, which probably you want to see very deep in the plane. So this is where the S-band receivers come in, higher frequency, lesser susceptible to scattering. You have an interferometer, so that means you have smaller beams, but you'll cover very little of the sky. And if you want to do a survey in a reasonable amount of time, you need to have a wider field of view. So you have a multi-beam beamformer, which can produce hundreds of beams in real time. And this is just a comparison here of what the single Parkes beam looks like compared to all these hundreds of beams that we have put. And you need a HPC where you can process this data. And this is where APSU's facility comes in with 120 GPUs capable of quasi-real-time searches. And what we actually do is we record the data, we search all these beams, we use the fact that we have multiple beams, we use that information to make decisions on what candidates to keep, fold, apply machine learning cuts, And this is the sad part. We are in this era now where we have to delete the data. Most of the previous surveys, we used to archive the data and repurpose things to death, and we still keep finding pulsars even now. But unfortunately, we're in an era where it's just too much of data to handle. So, and this is how next generation telescopes will also operate. So we are already there. Okay, so with all that in mind, this is generally how we go about, like, how the workflow looks like. Now I want to motivate why have we chosen these targets and what have we found. Globular clusters are areas where you have a lot of old stars. Old stars means, okay, probably a lot of them have found neutron stars, but they're also very dense. Order of 1,000 stars per cubic meter. So that's way higher than what you would typically find in the galactic field, which means a lot more interactions and a lot more interesting kind of binaries, which you typically don't find in the galactic field. And so with that in mind, what we did was we targeted a bunch of globular clusters. The way we selected it is some of these where we already know a lot of them, and which gives you an approximate DM range in which you have to search. So the DM dimension is reduced. You apply standard techniques, fast Fourier transform, and you're sensitive to binaries which are longer period binaries where you're assuming that the Doppler modulation can be approximated with a linear acceleration term. And then 300 beams on sky. And then with all that in mind, before we started operating the survey, before even FAST started operating, there were 150 pulsars in 28 clusters. And now we are standing at 345 pulsars in 45 clusters. So that's a huge increase. 106 of them have come from MeerKAT. Of course, if I want to speak about all of these 106 discoveries, I probably need the entire day. So I don't have that time. So I'm going to only be highlighting a few things. We have found very interesting things, right? From pulsars where you find these radio eclipses, highly eccentric pulsars, eccentricity of 0.9, exchange products. I told you about interactions where what happens is probably one companion recycled the pulsar and then got flung out for another massive companion. So we have found a lot of those kind of systems. Slow spinning, which you don't typically expect. And some of the discoveries have come from globular clusters where we didn't know the DM before. But I want to focus on one globular cluster, NGC 1815-1, where we found 13 pulsars recently, about 2-3 years ago. And one of them was quite interesting. If you plot the spin period with time, and if you have to model it for the orbit, you get a high eccentric orbit of 0.7 and a 7.4 day orbit, and 5.6 millisecond spin period. And if you take Kepler's equation, you get a minimum companion mass of 1.4 solar masses. Not only that, the beauty of pulsar timing, which I told you, where you can do very precise measurements, you can also be sensitive to post-Keplerian effects, where you're not only sensitive now to the Newtonian regime, but also to assumptions which only come from GR. So one thing you can do is measure the rate of advance of periastron, something what Einstein measured with Mercury, for example. And what we get there is a total mass constant of 3.88 solar mass. So you can do the math. M1 plus M2 is 3.88. M2 minimum is 1.4. So if M2 minimum is actually M2, that means M1 is really massive. So that starts becoming interesting. If you want to break the degeneracy, you want to find M1 and M2 like precisely, you need to measure other post-Keplerian effects. Unfortunately, we have not found a significant detection in those, but you can use probabilistic modeling to put some constraints on what could be the companion mass. What you have arrived at is something, at least a minimum of 2.09 solar mass and less than 62 degrees inclination of the orbit with 95% confidence. But if you look at the range of parameters which this companion mass can take, it's possibly in the mass cap. So it could be a very massive neutron star, or it could be a light black hole companion, which would make it the first pulsar black hole to be found ever. This is published in Science, so I highly encourage you to read this paper for further details. Okay, with that in mind, I want to move on to the next source. There is the Gamma Ray Space Telescope, which is the Fermi LAT, which is a large area telescope. which has been operating for a few decades now. And it turns out that there's a catalog of large range of sources, of which some have been found to be pulsars, but there are still, as you can see, order of 1,300 unidentified sources. And it's always motivating to go back and try to find pulsars here because you can understand more about the energetics of pulsars, the fact that they would emit in radio as well as gamma, what kind of energy budget is actually required for these things to happen. And more recently, a lot of them have been used to build a gamma ray PTA. So that's also something which has come into light quite recently. So how do you identify a good candidate to follow up in gamma rays, which could say, okay, it could be a pulsar? Roughly 2 parameters. You look at the variability. If it's something like an AGN, it's way more variable. So it should have less variability. And the curvature significance, which is how quickly does the energy fall off at higher frequencies, at higher energies of gamma rays. And as you can see, pulsars roughly occupy this space here. So that's what helps you stand out. And you can apply some clustering or machine learning methods to actually say that, okay, of all the unidentified sources, probably all of these could be pulsars. Let's go and put a telescope on them and try to find them. But the Fermi telescope is quite small. So the region where it is actually sensitive to is quite wide. And that's what is shown here in red. So this is actually the uncertainty region of where possibly the gamma ray source is coming from. And that is the 99% region. And so coming back to the radio telescope, the fact that we have multiple beams on sky, what you do is you put a lot of beams such that you at least cover this 99% ellipse region and try to see if hopefully you can find some pulsations in radio. And so that's what we did. We tracked around 85 sources, did a shallow survey where about 10 minutes and did multiple passes on it. And we have found at least 49 new pulsars. In fact, we found 3 new pulsars in the last couple of weeks. Most of them are millisecond pulsars. And a few of them are slow pulsars, but they don't have associations with the Fermi source. They're just background sources. And there have been a lot of papers that have come out from this. Again, I don't have time to get into the details, but I'll again highlight a few results. So one thing is, okay, why do you, I thought you're trying to find gamma ray pulsars here. Why are you going into radio? The point is this. It's easier to find things in radio. So once you find things in radio, you time them, you get an ephemeris, you can use that to go back to the Fermi data and fold the gamma ray photons. And that's what has been done for a long time, and it's been a very successful method of actually finding gamma ray pulsations. And we have found that for about half the pulsars have gamma ray pulsations. Not only that, a lot of them are these spider pulsars, and one of them, which is known as the red back, have what is known as orbital period variations. So you see variations in the orbital period. And the beauty is these things, if you look at this plot here, for example, which is the pulse profile, and this is the pulse profile tracked with time. If you actually want to get this kind of a straight pulse, you have to account for these orbital period variations. And this is what has been done. You have such a long baseline set, which has helped you be sensitive to these effects and actually model for them. Not only that, you can use information from optical to get constraints on the radial velocity, and you can use constraints from the orbital period from radio to actually put mass measurement constraints on the pulsar. And we now have one of the most massive pulsar constraints from this pulsar here, which is J2333. This is a paper which should be submitted soon, and stay tuned for that paper. So we have found a very massive pulsar here. And again, just to recollect, why is this interesting? It's because coming back to that plot where it puts constraints on the equation of state. All right, the third source, nearby galaxies. Why is it interesting? Well, we want to understand more about the fact that there are pulsars we know in our galaxy. Are there some similarities with things in the LMC and SMC, for example, in terms of neutron star formation, gravitational events, and again, trying to link FRBs and pulsars. So what we did is we went back to the images where we have found interesting regions within the SMC, which could potentially show pulsar wind nebulae, magnetas, and put a beam tiling on them. and try to see if we can find pulsars there. And what we have found is 27 new pulsars. 7 in the SMC, so that's doubled the population, and almost doubled also in the LMC. And again, a few highlights. Of the 7 pulsars in the SMC, 2 have pulsar wind nebulae associations, and one of them was also found to be glitching. So that's quite interesting. And in the LMC, we have found 20 pulsars, as I said, and one is potentially quite interesting. We have been tracking it for about 80 days, and it could be in a very long orbital period, order of many years. So we have still not been able to see the inflection point where it's actually starting to change. And so we still don't have a good constraint on what the orbital period is. The final source, which is supernova remnants, TeV sources, and pulsar wind nebulae. Again, it's a huge potential for finding young pulsars, the fact that pulsars are born out of supernovae. And there are a lot of sources out there. There are supernova catalogs where you can just go and follow up and try to say, okay, let's go and find some of these young pulsars. However, there are a lot of factors that come into actually detecting these pulsars. And this is to do with the fact that whether these pulsars actually beam towards us, which is the geometry, the luminosity function, the neutron star birth rate in our galaxy. There are a lot of things that go into it. So what we wanted to do is we chose a bunch of sources, applied different criteria based on the fact that if MeerKAT can observe them, possibly excluded CCOs, type 1A candidates, and something which can fit within the beam tiling of MeerKAT. And what we did is 134 targets, just one pulsar associated with a PWN. Okay, it's not so great, successful compared to what I showed before. But when you have a low success rate, it's a good opportunity to introspect and actually do population synthesis studies and try to understand, okay, what if I put in a synthetic population and put in a lot of criteria, and can I predict that I actually have got what I expected? So what was done is you simulated pulsars and then try to put a cutoff on pulsars which have a character stage greater than 100 kiloyears, because that's the typical dissipation time of the supernova remnants in the pulsar wind nebulae. And assign the pulsars with a certain size of the supernova and the birth velocity, track them with time, and then put the constraints on the fact that whether MeerKAT can detect it or not. And what we found is we can predict the number of discoveries, but what we did find is a lot of them which were missed is because they were too faint or too scattered. What we also found is just by switching from L band to S band, we could have probably recovered 50 to 150% more pulsars. So the bottom line is, if you're going to do the survey again, do it at a higher frequency and try to do it at a better upper limit than 52 microjansky. So hopefully those are some interesting results I showed you. I want to show some highlights which I've been working on recently. There is a project which has been running for a while. The first people who did this was actually the people from SETI, where you use volunteer distributed computing. You use host machines from all across the world to actually use their spare CPU and GPU cycles to do processing of data. This has been integrated for pulsar searching quite a while back. It was used successfully with the PALPHA and PMPS surveys and even found pulsars. And we have applied this now to MeerKAT globular cluster data. But we have still not found what it was initially designed for, which is these very compact binary pulsars, which are excellent platforms to do tests of gravity. So if you want to help us, please do sign up for this. And one other thing, with the MeerKAT data flow, the beauty is the way the MeerKAT architecture is structured is plug and play. If you have a particular science case and you can build a backend for it, you can come, the MeerKAT system allows you to do that. So we have actually gone ahead and done this and built a baseband recording system, which can record 4 petabytes of data. And with that data, you can do all kinds of things, FRB searches, pulsar searches, across a wide range of beams. So this is currently being done with a galactic plane survey as well as a globular cluster survey. So because of lack of time, I won't talk about it. And this slide is for Jayanta, because he talked about this a while back, which is incoherent beam subtraction. So it turns out that you can remove a lot of RFI baseline variations by just taking out the power from the self-correlation products. autocorrelation products from the beamform data. And it already helps a lot. It improves the RFI situation, and you can remove these baseline variations and you become more sensitive to much slower pulsars. So this is something we have applied and implemented, and this is working quite effectively right now. So in conclusion, I hope I've convinced you that this survey has found a lot of pulsars, very interesting things. 1,000 hours of observing across 5 years, it's coming to an end. But we still have a lot more to understand about pulsars. And the hope is we continue following up some of the interesting sources, and also learn with time as to what we should do for the next generation surveys. With that, I conclude. Thank you.
Thank you, Prajwal, for the excellent talks. Question.
So just one clarification and
Yes.
a question. So just to make sure I understand. So basically, if you use the ephemeris from radio data and search gamma ray data, the detection significance for pulsars gets enhanced, right? Is that right? Did I
It becomes
understand?
easier. So it's not that it's enhanced. So what typically is done in gamma ray pulsar searches is you can ideally use the entire length of data and try to do some kind of searches. But if you want to be sensitive to binary pulsars, your number of dimensions start exploding, and you just have to put in a lot of trials. So what you do is, if you already have constraints on certain parameters from radio, that reduces your dimensionality of your problem. Computationally it becomes easier.
Okay,
you can
so
do
computationally it becomes easier.
semi-coherent searches. You don't have to use the entire data set. You can use smaller chunks with these constraints, look for these gamma ray pulsations, and then you can go and fold back.
So my question is, has anyone found pulsars with DAMPE? That's another gamma ray telescope, Italian-Chinese experiment. Slightly less sensitive to Fermi.
What's the name again?
DAMPE.
DAMPE, no. I know something called, I think, Agello. I think that's probably another. No, sorry,
Agello is at Clemson. He's a faculty.
So not for Agello. Sorry. I think there's another one. Agile telescope, I think. Probably.
Agile is an Italian. That is KeV. Okay, so DAMPE is at GeV energy. Same energy range as Fermi.
That's your idea. Sorry. No, as far as I know, I'm not sure about. I don't know.
Less sensitive. It's not very sensitive, or
I don't know. I actually I don't know about this. So I have to look back. Yeah.
This is very cool. I'm completely new to pulsars. So I'm just wondering, how precisely do you know the locations on Sky? And is there any plans? And if it's not millisecond second level, is there any plans of doing like VLBI or EVN based follow-ups? To literally get the orbitals of some of these binaries.
Yeah, it's a nice question. So I didn't have time to talk about it, but pulsar timing already gives you a pretty good constraint on the position of the order of milliarc. I mean, not maybe milliarc seconds, but sub-arc second level. But then if you want to really get precise positions, there have been a few pulsars which have been followed up with VLBI, but this is something which is still being built up. A few of them have these positions, and so because of VLBI, you can get parallax measurements and you get better distance measurements. So one of the motivations why we want to do this is because the galactic electron density models are not as reliable as they are. And so the idea is, if we build this catalog of actual pulsar distances, that would also help improve these electron density models. So that's what we want to do in the future. Yeah.
Thanks.
Hey, hi. Thanks for that nice talk. I was curious about those gamma ray pulsars you showed in the slides. I could notice some of those pulsations are off in the phase with their radio pulsations. So I'm curious, is this physically coming from the same region, or was there any other reason of this phase offset?
Very happy that you asked that question. Just trying to find the slide.
Yeah, this one.
Yeah, so the short answer is we don't know. The fact that you can align, so what I've done here is what, not me, but like my collaborators have done is try to align radio and gamma and try to understand if this is the case. There are cases where we see them aligned, there are cases where we don't see them aligned. But one of the theories, there was a paper which came out actually just a few weeks back on Archive, which says that it's possible that the gamma ray emission is actually coming from a current sheet outside the light cylinder. This is one of the possibilities. But I would say this is still a topic of hot debate. We fully don't understand this. And doing these alignments has a very low margin of error. So sometimes you could also, these things could be completely wrong. So you have to take all these constraints into consideration.
Oh, okay. And also another question on that.
Yeah.
So how stable are these gamma ray pulsations compared to radio? Like you were talking about PTA kind of stuff with gamma ray pulsars as well. So how stable are they?
Yeah, so because if you want to build a PTA, you would choose pulsars which, just like in the radio PTA, which show these stable properties of timing across a long timing baseline. So I would say they're comparable to radio. It's just the only problem right now is it's not as bright as in radio. So the signal to noise is the issue. And that's one of the reasons why we don't have the kind of PTA constraints with gamma ray compared to radio.
Great. Thanks for that.
Yeah.
I have one question.
Yeah.
It's quite interesting to see there is a slow pulsar coming up in the globular cluster. So are they basically like kind of partially recycling one?
Yeah, so there are different opinions here. So one is possibly that there are probably white dwarf mergers probably leading to neutron stars, which are non-neutron stars, and with time they've evolved and you've found these slow pulsars. The other one is just a binary which has got disrupted with partial recycling. These things would only be understood better with P-dot measurements. And this is something I think for some of them, we still don't have it yet. And so it's still too difficult to say if it's one or the other. The other thing which would also help is proper motion, which would possibly tell if it's, if it's too far out from the globular cluster. So these are things which are still we are working on.
So I was wondering whether magnetic fields of them are actually higher than the typical MSP which you see in the globular cluster.
Yes. I have to look back. I don't know this actually.
Anyway, it's quite interesting.
Yeah,
yes. Pulsar population is coming up.
Yes.
Any more questions here or in the online? Okay. If not, let's thank Prajwal.
Thank you.